Hello and welcome back. Today we're going to continue with graph algorithms. Yesterday we looked at a fundamental algorithm, DFS, depth first search. And today we're going to look at its brother or sister or whatever, breadth first search. A breadth first search is a little bit of a different strategy. It's basically the same goal. It's going to explore the entire graph. It just goes about it a little bit differently. If you were to explore a maze, for example, you would try to go as deep into the maze as possible before you hit a dead end and then you started backing up. A breadth first search basically searches a perimeter. So, for example, if you have a missing person, right, and you last saw them in this building, then you would set up a search perimeter, that's 100 feet around that building. And then if you didn't find them there, then you'd set up another search perimeter 200 feet outside, a radius outside that building. And you would go further and further out until you found what you were looking for or you've exhausted all possibilities. And that's basically what breadth first search is. It explores each vertex that is closest to the initial vertex first, right? And what do I mean by closest? Closest here means distance, right? That is number of edges, not with respect to any edge weights, right? So you could, you start at this initial vertex and you're looking at 3 neighbors, right? You explore all 3 of those neighbors. It doesn't matter if that neighbor has a weight of 10 to get to. It doesn't matter if that, and then they've got 5 and they've got 2. You explore all 3 of those neighbors first, and then you go to the neighbors of the neighbors, right? So what we're going to do is we're going to start out with that same exact graph that we were using last time. And I'm going to walk you through the same basic process, but with breadth first search instead. To make it consistent, we'll go ahead and start at the same vertex here, I, and then we'll work out from that. And you'll see very, very quickly, but that you're searching this perimeter here, and you're going to get, first of all, you're going to get the things that are distance 2 away from your initial vertex. Then you're going to get, then you're going to explore things that are within its realm, right? Distance 2 away from the initial vertex, and distance 2 away from the initial vertex, until you get done with all of them. Okay. So I'm going to build a different data structure down here, and hopefully it's readily apparent what this is going to be. Remember that last time with DFS, depth first search, we used a stack data structure because it was keeping track of our breadcrumbs. This is kind of keeping track of our breadcrumbs in that it's going to this queue data structure, right? Let me rewrite that much better. Right? This queue data structure is going to keep track of what we still need to process and visit. Okay? We're going to keep track of the same artifacts. We're going to color our vertices. Again, white is going to be unvisited. Gray will be visited but not processed. And black will end up being processed and finished. Okay. Just a note here on the colorations. White, gray, and black are usually used because of traditionally printed textbooks. It's much cheaper to use grayscale than it is to use actual colors like red and blue or something like that. Not only that, but you get into colorblind issues with some individuals if you use some bad combinations of colors. So we'll go ahead and continue to use white, gray, and black here. We're also going to keep track of discovery time. And initially what we're going to do is we're going to keep track of the finish time as well. But immediately, or at least as we go through this, you'll discover that the finish time is actually not all that important. And you'll see why here in a second. Okay? So those are the things that we're going to keep track of. And I'll write them down just like we did last time. Again, it's arbitrary where you start. You can start at, we're going to start at an initial vertex I here. And what I'm going to do is I'm going to put that into the queue. Right? And when I do, I will mark that with the discovery time, saving the colon and then the finishing time here once we're done with it, and I will color it gray. Okay. Now what we do is that was just the initialization, by the way. Now what we do is we're going to dequeue it, right? And I'll put it over here. So current vertex. Now we're sitting at I here, right? So we can process it immediately or then look at the neighborhood, or we can look at the neighborhood and then process it. It doesn't really matter, all right? I'll go ahead and say that we're going to look at the neighborhood here first. We look at the neighborhood and we see that A and F are both connected to it. The order that you visit the neighborhood in, again, just like DFS, that can be an arbitrary order. It could be a lexicographic order. It could be, if these edges had weights 5 and 3, maybe I'll go to the least weighted edge first, and then I'll go to the larger weighted edges second, but instead of lexicographic order. Right? But for now, I'll just go ahead and go in lexicographic order. So I see A and F, and so I'm going to go ahead and put those into the queue. When I put it into the queue, that means it's been visited. And I will go ahead and color it gray and timestamp it with a discovery time. Likewise, F goes into the queue. It gets colored. And it gets timestamped 3. There we go. At this point, I am done exploring its neighborhood. And so I now process it. And whatever that means for you, ostensibly there's data being stored in these vertices. You process that data. Is this the thing I'm looking for? Or take that data and plug and chug, do whatever you're going to do with it, right? Your graph is representing something. What is that something? What are you ultimately trying to do here, right? So I will mark that as finished. Oops, sorry. I've already used 3. So 4, right? And then I will color it black. All right, it's done. Now you'll see here that the queue is telling me what I still have to explore and the order that I should explore it in. So I'm going to go ahead and dequeue A, right? And that's my current vertex. Now I'm standing on this vertex right here, and so I look at its neighborhood. Well, I is in its neighborhood, but it's colored black, so I don't visit it again. If I were to encounter a gray vertex in my neighborhood, I would not visit that as well, right? But I'm going to look at the neighborhood here, and I see C, B, and H, and so I will enqueue them in that order, in lexicographic order. B, C, and H. Mark them in the order that I discovered them, 5, 6, and 7. And then color them all gray because they're in the queue right now. Okay. At that point, I am done looking at its neighborhood, and so I process A. And that means, as far as the coloration here goes, I go color it black, it's done. It's already out of the queue because I dequeued it. Okay. Now I dequeue the next item, which is going to be F. And I look at its neighborhood. Again, I has already been visited. D and E are still white vertices, and so I will enqueue them again in lexicographic order, D and E. I will mark them. Oh, you know what? I never marked it with my ending timestamp, which was 8. There we go. And so 9 and 10. There we go. I've already enqueued them, and so I will color them gray. And now I will process F. And I'll represent that by coloring it black and marking it with a timestamp of 11. Okay. This is a queue, so let's make sure that our people in this standing in line move forward there, right? And on the next iteration, I DQ B. B is now out of the queue, and I'm looking at that as my current vertex. All right, so I see A, C, D, G, and A. Not H. I see A, C, D, and G. Right. One of them is black. I don't want to process it again. C and D, because they're gray, I know that they are in the queue already, that they've been visited, just they haven't been processed and finished yet. So I don't want to enqueue them twice. I don't want to end up processing them twice. And so the only white vertex here that has been unvisited is G. I'll NQ G. Let's see, I'm up to 12 now. Right. I will color it gray. And at that point, I'm done with it exploring its neighborhood. And so I will end up finishing B with a timestamp of 13. Right? And I think that was it. Right? Yeah, don't need that anymore. On the next iteration, I end up DQing C. I look at its neighborhood, and you'll note here already that everything has been colored either black or gray. So I'm not going to end up NQing anything further. I'm going to end up DQing, not NQing anything in its neighborhoods anymore, but I will end up processing them in that order. So C is next, and that will be 14. Then H is next, 15. D is next, 16. And the entire process, as I'm going along here, of course, I would be coloring these black. 16. And of course, I'm DQing them. I just fast forwarded there for you. At E, I would mark that as 17. After I've DQ'd it, of course. I would then mark it as black. Right? And then finally, G comes out of the queue, and it's marked with 18, and it's colored black. At which point I'm done, right? Now, one thing that I failed to notice here, or to keep track of, was the tree edges that you actually took to do this. So let me go ahead and reconstruct what we were doing there. We started at I, and then we went to its neighbors, right? At A, we went to all of its neighbors. Right? At F, we went to its neighbors, 9 and 10. Let's see, 9, 10, 11, it was finished, so 12 would have been next, which would have been G. Right? B, sorry. B came out next. And so I think it was this one. Correct me if I'm wrong, though. Right? But that's how we basically got through this graph here. All the timestamps, I believe, are correct. But that basically produces another kind of artifact, like similar to the DFS that we did yesterday, but it's a BFS tree instead. Right? So here's our BFS tree. Right? We started at I. We went to A and F. Right? These were tree edges. Right? From A, we went to B, C, and H. B, C, and H. From F, we went to D and E. There we go. And then, yes, in fact, we did go to B next. Why? Well, you can look at this top to bottom, left to right. This is the order that we visited things in with respect to the BFS tree. So once we were done with E, we came back around to B and then processed its neighborhood. But the only thing left was G. Right? 5, 6, 7, 8, 9. 9 vertices, and we got them all. What about the other edges? For example, what about C to D? C to D, well, that looks like this, right? That's a cross edge, right? It is. They're not. These aren't siblings of each other's. These are cousins of each other, and they're being connected by this this edge that's not part of the BFS tree. It's not a tree edge, so this ends up being a cross edge. What about C to D? C. Oh, sorry, that was C to D. C to B. Sorry, right? There's another cross edge, right? B to D. I already got that one. C to B. Yep, C to B. C to D. B to D. There we go. Cross edge. Oops. Cross edge. D to G. Cross edge. And G to H. Also a cross edge, right? So all of the others were cross edges. Why didn't we get any forward edges or back edges, right? A forward edge would look something like this. Let me go ahead and put it in red here. Right? What if we had a back edge going from, remember, back edges, forward edges in an undirected graph are going to end up being the same thing because there's no orientation. So call this a back edge, call this a forward edge, whatever you want. Why can't we have something like that in our BFS tree here? If that edge were there, if I were connected to B, then we would have explored it when we explored I's neighborhood. This is not possible, right? This cannot happen. We can't have forward edges or back edges in an undirected graph of a BFS tree. Okay? Good observation there. You can only have tree edges and cross edges. What does the cross edge tell us? What does this cross edge tell us? Well, it's a tree, so it's connected. You can go from D, traverse back up to the root. From the root, you can get to any descendant node. But then also you've got this cross edge going across. Guess what? You have a cycle. Right? So cycle detection. Right? We've got a lot of applications that we can now use in our BFS, or we can use BFS or DFS on. Before we talk about that, though, let's go ahead and develop an actual algorithm, pseudocode, for what we just did. Okay. First of all, I'll make the observation that if you have an this will work for directed graphs or undirected graphs, but if you have a situation where you've got an undirected graph and then it's a forest, disconnected components, right? Not necessarily a forest, but disconnected components. Just like DFS, you might have to restart it. If you have a situation where you've got a directed graph, say, let's say we are able to go there, there, and there, right? And I don't know, down there. So A, B, C, D, and E. And I have the unfortunate chance to just start my BFS at A. I would end up exploring B. I would end up exploring C. Now at C, I would not go to D because this edge here is an incoming edge. I would only explore the outgoing edges from the neighborhood. And so I would end up going down here, leaving D to be unexplored. So I may have to restart my BFS if there is any unexplored vertex, any vertex that still remains white after building this BFS tree. Okay? All right. So if you want to, you can go ahead and check out the lecture notes for the main algorithm. Basically, it just initializes everything to white, and then it goes over each one of them, kicks off a BFS starting at this particular vertex, and if it has to, once that's done, it looks for any other white unvisited vertex, and then restarts the BFS at that point. But what I want to do is I want to focus on the actual BFS itself. So our input will be a graph. G equals V comma E. And again, it could be directed or undirected. This will work either way. And an initial vertex. That's where you start. X. Okay. and our output will simply be just the BFS exploration of this. So what I'm going to do is I'm going to set my counter here. I'm going to add 1 to it. Remember, we might be starting over, right? Actually, I'll just go ahead and go with ++ here, right? The counter might have been set in the main algorithm, and then when it had to restart, it wanted to keep the same counter. And so we're going to increment it when we come into BFS here. Each iteration, we're going to increment it, but otherwise it was initialized in the main BFS routine. By the way, I'm not going to keep track in the pseudocode on here. I'm not going to keep track of the finishing time. Why? Look at the discovery times. 1, 2, 3, and then B was next, 5. And then C was next, 6, 7 for H, then D, then E, then finally G. Remember, it was this order over here. Well, what about the finishing time? Remember, a queue is a first in, first out FIFO data structure. And so necessarily, if things go in a certain way, they come out in exactly the same way. So the finishing times are also going to be 4, 8, 11, let's see, B, 13, 14, 15. They're not going to be contiguous numbers because we're using the counter for both of these things, but it's kind of useless. The discovery times, this discovery sequence is going to be exactly the same as the finishing sequence. So I'm not going to keep track of both of those things, okay? I am going to initialize an empty queue. Right? I will mark X with discovery time, with counter, excuse me. This is, again, the discovery time. I will color X gray because we've now visited it. And then I will enqueue it. Q.enqueue X. Right? That's the initialization. That's where I'm starting at vertex X here. You'll note here that I stopped this algorithm not once everything was colored gray, but once the queue became empty. Right? So that's what I'll do here. While the queue is not empty, ... I will take the next thing out of the queue. I've already used X here, so I'll use Y. No, I don't want to use Y either. I shouldn't have used X, but I'll go ahead and use, you know what? Let's go ahead and update that. X, 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 X. I'll start it with initial vertex. Usually we use S. I'll use U here. U, U, and U. There we go. Because I want X down here. X is going to be Q.dequeue. Right? Remember, it is spelled with UE. DEQUE by itself is a DEC, and that is a double-ended queue. So it is UE. Right? I'm pulling the next thing out of the queue, and then I'm looking at its neighborhood. For each Y in the neighborhood of X, right, in some order. And again, that could be lexicographic, it could be based on the edge weights, it could be based on random chance, right? Whatever you want. It really doesn't matter. If Y is white, that is unvisited, then I will go ahead and put it into the queue. I'll increment my counter here. I will mark Y with count because that's where I'm discovered it. I will color Y with, or color Y, excuse me, gray. Right? And then finally, I'm running out of room here, so I will go with q.nq y. There we go. And that's the end of my for loop. It's not the end of my while loop. So I'll go with ... And over here. This is still in the while loop. So ... There we go. And what I'm going to do is I'm going to increment my counter. Because if I want to do processing, I'm gonna skip this actually, and I will process X and color X black. It's been done. If you really wanted to, of course, you could increment your counter here again and mark X with a processing time if you were keeping track of both of those. But again, it's kind of useless. It's going to give you the exact same processing order, top to bottom, left to right. Right? Both of those are going to be the same. Okay. Okay. Now that we've done both BFS and DFS, let's go ahead and do a quick analysis. Forgive me for a little bit of hand-wavy analysis, but I'll do a really quick analysis to understand it. And then we'll start looking at some actual applications of both of these things. Okay. So, analysis. Right. Actually, before we do that, let's note down our observations from before. Right. So in a BFS tree, for undirected graphs, no back or forward edges are possible. Right. If you had a back edge or a forward edge for an undirected graph, then it would have been closer. And it would have been in the neighborhood of that vertex, and you would have explored it already, right? In a BFS tree for directed graphs, back edges are possible, but again, no forward edges are. Right? With BFS, the finishing and discovery orders are the same due to the FIFO nature of the queue data structure used. UE, there we go. Cross edges. This is another observation that I'll just tell you about, and then I'll let you think about it. In a BFS tree, connect cousins and aunts and uncles, but never descendants or ancestors. Right? I'll let you think about that on why, and I don't know how to spell descendants, but I'll just leave it like that. It might not. I mean, basically, that's going to be a forward edge, back edge if you really think about it. But I'll let you go ahead and think about that, right? And of course, BFS may need to be restarted if it is disconnected for undirected graphs, or you could have a situation like I just showed you before with that one example, or it is directed and some edges or some vertices are not reachable from other vertices, right? And you'd have to restart it. Okay. So now let's talk about the analysis. Right? So my first observation is that both DFS and BFS only process each node exactly once. Right? So if that's your idea of an elementary operation, the actual processing of data, then you're done, right? If your elementary operation is the processing of a node, and there are n nodes, then both are order n. Right? And that's pretty straightforward. You make sure that you process everything, all n of them, you make sure that you only process it once, and that's it. You're done. And that's actually my personal preferred way of looking at it, in that that should be the elementary operation, right? Traversing an edge or stepping onto a vertex, those are kind of necessary for the control structure of the algorithm. Just like we don't look at the increment of an index variable in a for loop, I prefer not to look at those things that are necessary for the control structure of the algorithm. Instead, you're doing something. You're not just doing BFS or DFS in practice. You're doing some processing of the data stored in the nodes. And if you're only ever processing a node once and then it's done, then clearly it's going to be linear. Some people do like to look at other elementary operations. For example, if visiting a node or traversing or examining an edge is your elementary operation, then it's a little bit more complicated. It becomes, well, you could end up elementary operation. Sorry, there we go. So consider one particular edge, right? It's incident on two vertices. So from that first vertex, you look at that edge and traverse it in order to look at its neighbor and decide it's gray, it's black, or it's white, so I need to do something with it, right? Either put it into the queue or put it into the stack or something like that. And then again, you'll do that a second time when you're processing the other endpoint and you're looking back at where you came from or something that you've already processed. And, oh, okay, well, yeah, sure, I need to examine that. I need to traverse that edge to see that this is gray or this is black or this is white and make a decision. So every edge, because it's basically a handshake, kind of like the handshake lemma, if you remember that, that every edge is incident on two vertices, and so you look at it twice, basically. And consequently, you might also look or examine the vertex more than once, because the first time you see it, you color it white. You might see it again and again and again for each one of those edges, but to see that it's gray and that then you ultimately ignore it. But you might examine those vertices multiple times, but only twice at most for each edge that's in the graph. So you can go ahead and come up with the following analysis, that it's going to be order whatever the size of the vertex set is here, plus the size of the edge set. And then there's a 2 in front of each one of those if you want to. But again, big O analysis, we throw those out. So ultimately, since we use n and m to describe those things, it's going to be order n plus m. I don't like that because it's a little bit more complex than it needs to be, because now you have to take into account, is it a dense graph? In other words, recall that n is order n, m. Let me LaTeX it here. Is order n squared. If I've got a graph with n vertices, the maximum number of edges that it could have is going to be order n squared. Again, kind of like the handshake lemma, where how many pairs can you make? N choose 2. That's how many edges you can make into that graph. That would be called, if you have like a lot of edges, then it's a dense graph. You could have a very sparse graph, like a tree, where the number of vertices is roughly equal to the number of edges plus minus 1. And so it's going to be order not n squared, but m is going to be order n, right? In which case, it doesn't matter. If you take one of those for sparse graphs, whatever that means, m is going to end up being order n, right? And so BFS, DFS is order n. And we're right back to where I started, by observing that you only ever process a node exactly once. For dense graphs, m is going to be order n squared. And so BFS, DFS becomes order n plus n squared is going to be n squared. Right? But not only that, the way that you represent the graph also comes into play. Examining or traversing an edge or computing a neighborhood of a vertex to even decide what are its neighbors and do I need to look at them may have different complexities based on the graph representation. Right? Think about this really quickly for a moment here. If it is a matrix, I want to gather the neighborhood of a particular vertex. I need to look at the entire row of that matrix. And so 0, okay, ignore it. 0, ignore it. 0, ignore it. 1, oh, okay, there's a neighbor, right? So I would potentially need to go over n elements in that adjacency matrix in order to even determine what the neighborhood is. That's going to lead to order n. And then if you're doing that multiple times, then of course then you get back to order n squared here, right? If it were an adjacency list, then that means that the neighborhood is already there for me, right? That only the neighbors are actually in the list for that vertex, and I don't need to compute anything, right? Iterating over it, of course, is going to be the size of the neighborhood, which can be order n, but it's only going to be ordered the degree of that node. If I did that over and over and over again, though, then basically it devolves into order E, where E is the number of edges in your graph. So there are subtleties that don't really need to be there. They overcomplicate things. Again, if you look at it from the idea that you are processing a node exactly once, then it's going to be order n. Oh, okay. Privacy Badger. All right. Thank you, Privacy Badger. Good job. Although popping up, you're not making a good name for yourself there. I've got Privacy Badger in my my browser, all my browsers, and they just popped up saying, "Congratulations, 10,000 blocked ads." Great, but pop-ups are exactly why I installed you. You're defeating your own purpose there, right? All right, sorry. It just caught my eye over there. All right, let's talk about applications. Okay. First application is going to be connectivity. All right. Given two vertices, x and y, in the vertex set of a particular graph, determine if there is a path between them. In other words, if I start at x, can I get to y? If I start at y, can I get to x, right? And that's going to be pretty simple, right? A DFS or a BFS, all you have to do is start at one of those endpoints. Build your DFS or your BFS tree. In fact, you don't even need to build the tree. Start at x, perform your DFS, and if you ever see y, immediately stop and answer yes. In fact, the breadcrumbs that you've set so far in your stack or in your not necessarily in your BFS, in your queue, so DFS is probably more appropriate in this case, but the breadcrumbs that you've built with your DFS, that in fact gives you a path between those two nodes. So not only could you do the decision version of this problem, yes, no, there is a path, there is not a path. You can actually do the functional version and output a path if one exists. It works for directed or undirected. Right? Another thing that you can do is topological sorting. Given a poset, that's a partially ordered set. Hopefully you remember that from, say, discrete math. A partially ordered set is one that is reflexive, anti-symmetric, and transitive. So if you don't remember what that means, that's fine for now. You may want to go back and review that. But otherwise, it's basically a DAG, right? I.e. a DAG. A DAG is a directed, acyclic, graph, right? There are no cycles in it, but it's directed. So if you took away the orientation, you could have a cycle, but that actual direction of the cycle is not there, right? So what does topological sorting mean? It means imposing a total order on the set. Right? So let's go ahead and take a look at an example here. So I'll go ahead and go with, I don't know, oops, maybe something that looks like this. A, B, C, D, E, there we go. And like this. This is a post set. Now, generally, what you for actual post sets, you describe these as a Haas diagram, where you take everything is reflexive, and so you have these self edges here, but you usually don't draw them because it's understood that it's a post set. You also have these transitive relationships. I can go from A to B and B to C. Therefore, I need this relation here, right? But you generally, again, don't draw them, right? They flow one way. If I had an edge going back over here, then that's not a DAG because there is now a cycle. Go from A to B, B to C, and then C back to A, right? So I don't have cycles here in a post set, but I do have relations. Now those relations connote some precedence, right? That A comes before B, right? That B comes before C, and by transitivity, A comes before C, right? This could be less than or equal to, more accurately, because of course B is less than or equal to itself, right? That's where reflexivity comes in. But some things are incomparable, right? So for example, does, let's say, B come before D, or does D come before B? Which one is it? Well, the way that I wrote my DAG here, this post set, these are incomparable. I don't know. B could come before D. It doesn't matter. D could come before B, right? So who cares, right? That's not part of the relation. It's not a total order. A total order would mean that everything has a well-defined relationship. I can go from A to B to C to D, right? That's a nice post set, right? That's a nice total order here, right? This over here is a partial order because some things are not comparable to each other. A total order, everything is comparable to everything else. And so we like total orders. Think about using total orders all the time. In fact, lots of people encountered this when they did Huffman coding. They put stuff into a heap, and then they immediately had some problems because Python came back and said, well, you can't compare a node to a string. You have to compare strings to strings. I know how to do that, Python says. You can compare numbers to numbers. You may even be able to compare numbers to strings, but different types, I don't know how to do that. So what you had to do is you had to help Python out by saying, all right, here's a tie. I need you to break ties using this other thing over here that you know how to do, right? It doesn't matter if you put these two trees together first or those two trees together first. It'll lead to an equivalent Huffman code. But for the purposes of this algorithm and for Python to not complain about it, I need a total order. I need to take a partial order and I need to transform it into a total order, right? By saying, all right, B comes before D. Right? I'll just say that I'll just impose that ordering on it. Or equivalently, you could say, all right, B comes before D. D comes before B. I don't care, right? But the point is that you want to take this partial order and you want to transform it into a total order. Right? DFS is your solution. Right? So perform a DFS and take note of the finishing times, I believe. Yeah. Let's see. Yep, finishing times. All right, so let's do that. I'll go ahead and start at A. You can start at an arbitrary vertex. It doesn't matter. You might have to start over. For example, if I started at C over here, then I would only ever explore C, finish it up, and then have to start somewhere else. So I'll make it a little bit more straightforward here by starting at what I know is going to... Actually, let's go ahead and make it interesting, and I'll start at B here. Right? And I'll note the discovery times here as 1. Right? Now from B, I don't go back to A because that's not really in its neighborhood. I only look at outgoing edges. And so I will explore to C, at which point I'm at a dead end and I start backtracking. So 3 and then 4. I have to start DFS over because I have unvisited vertices A, D, and E. So now let's go ahead and start over at, again, an arbitrary vertex. It really doesn't matter. 5. That's the discovery time. I go to D, 6, and 7. All right, for E. I do see it in my neighborhood here of D, but I see that it's already been colored black, and so I don't visit it anymore. And then finally, when I'm now I start backtracking 8, 9, and 10. Right? So take note of the finishing times here. The finishing times are going to be the second number there. 10, 4, 3, 8, and 9. And if I sort them in descending order, right? So let's go ahead and note them. A is going to be 10. B is going to be 4. C is going to be 3. D is going to be 9. And E is going to be 8. And if I sort them in descending order, then I get A, 10. I get D, 9. I get E, 8. B and C, 4 and 3. Right? There gives me a total order that is consistent with this partial order over here. Just simply you put those into a line. A to D to E to B to C. There. That total order is consistent with this. A comes before B, and so therefore A comes before B in this ordering over here. You can do that with any pairing there. Now B and D again are incomparable, and so I could have put B first. I could have put D first. This algorithm just made my decision for me by virtue of where it started, the initial vertex that it started at, and where it went next. Okay, so there, that is a direct application of DFS. You can transform a poset, a partial order, into a total order, and that's called topological sorting. Okay. And again, what you do is you run DFS and note the finishing times. Right? Sort them in descending order to get a total order, total topological order out of it. Right? There. Right. So why doesn't Python do that for us automatically? Who knows? It could, but maybe there's a decorator pattern out there that would throw in that kind of functionality. Right? Another application is going to be cycle detection. Right? And you're going to have to do a lot of this, some of this stuff in your actual programming, that you're going to have to detect that there is a cycle in this graph. There is not a cycle in this graph. And it's pretty easy because we already noted that if the presence of a forward for undirected, the presence of a forward or back or cross edge implies a cycle. Right? Now, it doesn't necessarily give you the biggest cycle or the smallest cycle, right? But it gives you a cycle. So that's a decision version. Here's a graph. Does it contain a cycle or not? In other words, here's a graph. Is it a tree or not? Right? Or a forest or not? All of those questions can be answered by running DFS or BFS and checking to see if there's a forward or a back or a cross edge for undirected graphs. For directed graphs, it gets a little bit more complicated, especially if you want to use BFS. But if you use DFS, it's super simple. If you ever have a back edge, right, going back up, there's your cycle. Right? So pretty straightforward. Another application is bipartite bipartite testing. There we go. All right. So given a graph G, is it bipartite or not? All right. Again, another decision version here. So let's go back to our tablet here, and let's understand what a bipartite graph is first, if you don't remember. A bipartite graph is one that can be split into two parts, a left partition and a right partition, and there might be vertices between those two parts, or in each one of those partitions, but edges only connect between those two partitions, right? And never within. So you don't have something like this. You can't have an edge like that. Otherwise, it's not a bipartite graph, right? So a lot of times, the left partition and the right partition is also identified with colors. Right? Blue and, say, red here. If there are any colorblind folks out there, please let me know. I don't know if you might have like a YouTube plugin or something that would correct for color blindness. Go ahead and check that out. But otherwise, let me know what I should stay away from. Because I'm not an expert on color blindness. Please let me know. All right. So I've got a left partition and a right partition here. All the nodes over here in the left partition could be colored blue. All the nodes over here in the right partition could be colored red. And we know that it's a bipartite graph. However, it would not be a bipartite graph if we had an edge that connected a red vertex to a red vertex, or a blue vertex to a blue vertex, right? Those two things would not be allowed. Right? That gives us a way to detect whether or not something is bipartite. All right? So let's go ahead and use that other graph that we were using before. Yeah, this graph. Okay. I'll cover that up over there. Now, is this a bipartite graph or not? What we're going to do is we're going to run DFS on this. But instead of, in addition to, or instead of white, gray, and black, I'm going to keep track of those two colors, red and blue. I'll go ahead and start out with blue. If I start out at I, I'll color that blue. I'll look at its neighbors. In fact, you could use BFS here as well, right? And I will color all of those red. Then, when I go to, let's say, just say that it's BFS here. When I go to the next vertex here, then I color all of its neighbors blue. Right? Let's go with blue here. Right? There we go. There we go. And there we go. And we immediately see, we immediately see, but later on in the algorithm, when we get to B here and we look at all of its neighbors need to be red because of the nature of, because of the nature of bipartite graphs. That you can't have a blue connected to a blue. Ah, darn it. I just lost all my highlights. You know what? I could go, there we go. Undo. So, this right here kills us. A blue cannot be connected to a blue. Another way of observing this is that there is a cycle involved with these two, and A, that is odd. Odd length cycles. Something is bipartite. G is bipartite. If and only if it contains no odd length cycles. Otherwise, if it has an odd length cycle like 3 or 5, here's another example. 1, 2, 3, 4. Let's see. 1, 2, 3, 4, 5, 6, 7. All the way around there. That would also kill us for being bipartite. Because if we alternate the colors for this, red and then blue over here, red, blue, red, blue. Actually, that 1, 2, 3, 4, 5, 6, 7. Did I screw up somehow? 1, 2, 3, 4, 5, 6, 7. Blue, red. Oh, yes. What about this one right here? All right. Is it blue? Well, then that violates it with E. If it is it red, then that violates it with its other neighbor. I just didn't color D right there. Right. So you can use DFS or BFS to do this by keeping track of another color. And that also, because of this theorem right here, it also tells you whether or not there is an odd length cycle. Right? Or that all cycles are of even length. Okay. You can also do what's called a condensation graph. Again, to go back, why do we care about this stuff? It's because we look at different types of graph classes like bipartite graphs or trees or Hamiltonian graphs or Euler graphs or whatever, because if we restrict our attention to those things, then we have this whole suite of theorems and algorithms that suddenly become efficient on those types of graphs. So if we can take a problem, observe that it can be modeled by a bipartite graph, then that means that we can bring this entire tool set of algorithms and theorems to bear on that problem and know something else, more fundamental about that problem. Right? Condensation graphs are another application that allow you to take a very complex graph and condense it down into a much simpler graph where the topology may be much easier to look at. Basically, it collapses a large complex graph into its strongly connected components. It's a way of simplifying the graph topology by cutting out unnecessary or redundant information and simplifying it down. You do this all the time in mathematics. These are called isomorphisms, homeomorphisms, homomorphisms, etc. You're basically mapping one mathematical object onto another mathematical object, but preserving some property in that process. In this case, we're preserving connectivity. That if A or X is there's a directed path from X to Y, there will still be a directed path from the representative of X to the representative of Y in this condensation graph. All right. It allows you to take a large graph and then have a much more compact representation of that graph. Before we look at an example, we note what a strongly connected component is. Right? So two vertices are strongly connected in a directed graph G if there is a directed path from X to Y and from Y to X. Right? So the idea here is that if I start at this vertex X, I can get to Y. I'm not painting myself into a corner. I am not, because I have a directed path back to where I started. Right? In other words, I also have a cycle between those two vertices. Right? Well, if I can go from X to Y and Y to X, then, for example, if I'm broadcasting a message and X is strongly connected to Y and Y is strongly connected to X, I only have to make sure that one of those nodes gets the message, and then I've got some assurance or something that X will forward it to Y and Y will forward it to X. Right? It's kind of like an old school calling list where you've got a group of 100 people. You don't want to call them all. Instead, you distribute the work. I'll call these 3 people. Those 3 people will call their 3 closest friends, etc., and so on. And then that group or that clique of people, they all get the message with minimal amount of work that falls to one person. Okay. So a strongly connected component is a subset of vertices that are each strongly connected to each other. All right. So we're going to illustrate this with an actual example. Okay. And let me go over here. All right. So of course, as I implied, it is going to be on a directed graph or a digraph. Now, this is not a directed acyclic graph. This is not a DAG, right? Because in fact, we do have a couple of cycles here. Here's the simplest cycle. You can go from D to G, and you can go from G to D. That's a cycle of length 2, right? You also have other cycles here. You can go from, let's say, B to C, C to F, and then you're stuck, I guess. So here, E, C, B, and then E, and then you can there's your directed cycle for those three. So you can see that this is a cycle graph, or that this is a graph with cycles in it. Okay. So we're going to create what's called a condensation graph out of this, but the first step is that we're going to run DFS on it. Okay. We're going to keep track of the finishing timestamps here. So I'm not going to keep track of the discovery timestamps, just the finishing timestamps, just to make sure that this doesn't, get out of hand here. I'll go in lexicographic order. Right? So 1. Right? I've discovered A, and I look at its neighborhood here. It's connected to D, B, and E. I'll go in lexicographic order. I'll go to B. 2. Actually, I am keeping track of both here. Oh well, good practice. All right. I look at its neighborhood. Now remember, the neighborhood in a directed graph is are only the vertices that go out of it, that are adjacent from it, not this edge right here. Right. So I'll go to C because that is lexicographically next. From C, I could go back to B, but of course it's already been discovered. I'm omitting the coloring here, the white, gray, and the black, just for clarity. From there, I could go to D, or I could go to F. And so I'll go in lexicographic order again. D. From D, I can go to G, so 5. And then from G, I can go to F, 6. At which point I am sunk. In fact, we call these sinks. If you only have edges, incoming edges, then you're called what's called a sink. If you only have outgoing edges and you can never actually get to A, then you're called a source vertex. So a source vertex, a sink vertex. If you have stuff going out and in, then you're neither. You're something else. I don't know what we call those things. Right. We finish this at 7. We backtrack to G and finish that at 8. We backtrack to D and finish that at 9. We backtrack to C and finish that at 10. We backtrack back to B, but we don't finish that. I'm back here at B. I've already explored that direction, but I haven't explored this direction. So I go there next. We are up to 11. And that's not a sink, but I've already finished processing C, excuse me. And so I end up with 12, 13, and then finally 14, backtracking all the way to A. So I'm noting all of the finishing timestamps here. Now what we're going to do is we're going to reverse the graph. Okay? So let me go ahead and put... Actually, no, I'll just draw it over here. Right? Can I do this? I'll give I'm just giving myself some more room here. Right? All right, so A, B, C, D, E, F, and G. I'm going to do what's called the transpose graph of this. Remember that a graph can be represented as a matrix. The transpose of a matrix is you go along the diagonal and then you flip it. What that means for a graph is simply reversing all of the orientations of all of the edges. Right? So instead of going from A to D, I'm actually going from D to A. Instead of going from A to B, I'm going from B to A. And instead of going from A to E, I'm going backwards. So all these edges are still there, but they're going in the opposite direction now. Right? This is the second step of this algorithm. Right? And then up, over, and then both of these are here, but I will reverse them. There we go. And finally this one. Right. This is the transpose graph. Okay. Now what we're going to do is we're going to run DFS on it. And in, let's see, I think we have to, in order of finishing timestamps, right? So we're going to, instead of going in lexicographic order now, what we're going to do is we're going to go back and find the finishing timestamp of each one of these things. So the lowest one here I observe is 7. So in other words, we're going to start at F. Okay, is that right? In reverse order, I think. Pardon me. I'm going to have to. I want to make sure that I get this right. Descending order. Sorry, and so yeah, I thought that was wrong. Let me restore this. That's 7. So, step 1, DFS. Step 2, compute the transpose graph. Step 3, perform a DFS on transpose, the transpose graph, in descending order of DFS finish timestamps in number 1. Okay. So descending order, that means that we start at A. Right? So let's perform a DFS starting at A here. And here, since I've used black down here, I'll go ahead and do red over here for discovery time, and then of course finish time as well. Why did I immediately mark that as 2? It's because now in A was a source before, and now it becomes a sink. There is no way to get out of this neighborhood. So we're done. Right? Now, each time we start over, that is a connected component. Let's go ahead and take a look at the original graph over here. From A, I can go anywhere. I can pretty much go anywhere. But from anywhere else, am I able to get back to A? No. A is its own strongly connected component. If I'm at A, I am stuck. I can't go anywhere. I can't come back to it. I can get out of it, but I can never come back to it. So it's its own strongly connected component. Let's go ahead and go with the next one. So I'll restart this, and I'll restart it at the next one, which is B here. So 3, colon. Now from B, I can go to A, but it's already been processed. From B, I can go to C, so that's where I go to next. 4. From C, I can get back to B, but it's gray. I don't want to process it again, but I can get to E, and so I'll go ahead and go with 5 here. Right. From E, I can go to B, but that's gray. I can go to A, but that's black. So I stay here. I start backtracking. Process that. I backtrack. There's nowhere else to go from C, so 7, and then 8. And ultimately, I have to start over again. But B, C, and E, they're all in their own strongly connected component here. B, C, and E. So I'm collapsing them down into one node. Within this node, I can get to B. From B, I can get to C. I could get to E by maybe going through C and back and forth. In other words, these 3 things are strongly connected. From any vertex in there, I can get to any other vertex within this component. I'll also observe that from A, I can get to that strongly connected component in a couple of ways here. I could go to B, and then I could traverse within that strongly connected component. I could go to E, and then traverse within that strongly connected component. So I'll also draw this edge right here. But I will not draw the back edge, because from any one of those 3 vertices, I can't get back to A. Right? Let's continue. So that's been these have all been taken care of. Among the remaining vertices here, the next one is going to be D, because it's 9. So I'll restart my DFS over here at 9. Right? From D, I could get to C, but it's already been processed. So I'll go down to G, 10. From G, I can get back to D, but it's a gray, so I don't. Right? 11 and 12. And there's my next strongly connected component. D and G. Every time you restart your DFS in the transpose graph, that tells you that whatever you visited in that phase is a strongly connected component. From B, C, and E, I could get to that component as well in the original graph. And as you can imagine, the last one to be visited here, 13, it's now a source. And so, but everything has been visited around it. So F is its own strongly connected component, because in the original graph, it was a sink. I can get there from either one of these components. Right? Yeah. And by transitivity, if you want to, you can go ahead and do it like this. But it's not necessary because you can go from A to this strongly connected component, and then this strongly connected component, you can get over there to F. But I'll go ahead and keep that there. This resulting graph here is called the condensation graph. It's been condensed down into its essential parts, its strongly connected components. Now you can. This is a small example, of course, because we did it by hand. But we took a 7 vertex graph and we condensed it down into a 4 vertex graph that is also a DAG, directed acyclic graph. The original one contained cycles, right? Cycle, cycle, cycle everywhere. But the condensation graph will, of course, not contain any cycles, because if you had a cycle in a condensation graph, you would have collapsed that into a strongly connected component. So it gives us a way to look at the topology of a complex graph in a much simpler graph, taking away cycles, fewer vertices here, etc. So it gives you a way of, again, this is a small example. You can think of a very large example, like the topology of the internet or something like that, or the topology of 1 million people, where there's a directed relation. If this person knows this person may not necessarily know that person, right? Or something like that. Dealing with a graph with 1 million vertices can be quite complex. If you can get an equivalent graph, equivalent in some sense, in this case, the strongly connected components are preserved, and take that 1 million node graph and take it down to a few hundred nodes, awesome. Now all of our algorithms can run efficiently, right? Or quickly at least. And so that is a way of preserving those kind of properties, but speeding up the efficiency in some things, right? It could also be, modeling a network and broadcast messages or something like that. You can simplify your network, and now you don't have to lay so much wire, or you can use fewer routers or something like that. Right? All right. Any questions? I don't see any questions. Nope. All right. So we'll continue with more applications tomorrow. A quiz review tomorrow as well, because it's Friday. But otherwise, hopefully you've got a good start on programming for assignment 3 on all these graph algorithms. Right. Have a good day.